Our project was over the effects of geometry and architecture of PMCs on acoustic emissions. This project was designed to study how varying geometry and architecture type of polymer matrix composites affect the acoustic emissions measured while said structures experience tensile stress. These types of PMCs being tested are used for aerospace structures such as nacelle surroundings on jet engines. Specifically, this study desires to establish an empirical relationship between the thickness of a PMC and energy attenuation, as well as subsequent frequency content experienced during tensile stress testing. Each test subjects a PMC of distinct ply thickness and internal weave structure to determine the damage modes for each sample. Additionally, the peak frequency of the propagated acoustic emission signals with respect to the time domain will be measured. Tests are conducted to determine the relationship between the frequency centroid of acoustic emission signals and observed damage modes, and to understand how the frequency centroid of acoustic emission interacts with the propagation distance of the signal. Straight-edge PMC samples of varying architecture and geometry will be subjected to a tensile test of constant pull rate until catastrophic structural failure is achieved. Two distinct double-notch configurations and a single hole configuration will be used to persuade break localization, so that sensor placement can be consistent throughout experiment trials. For our experiments, we were given 6-ply, 9-ply, 12-ply, and 2 laminate panels. Each panel had a varying thickness. Each sensor was attached a distance from the center of the specimen. Sensor 1 was 15 millimeters, sensor 2 was 30, sensor 3 was 45, and sensor 4 was 60. Each panel was cut into 10-inch long strips, and each specimen was cut 1.5 inches wide. Samples either had a 1/4 inch hole cut into the center or had 2 notches 3 millimeters deep and 0.5 millimeter wide cut into the sides opposite of each other. 2 sets of notch tests were done. One set had notches in the center of the specimen, and the other set had the notches located at the top of the specimen, 80 millimeters from the center. A test matrix was completed detailing the samples that are being used in the experiment. Each specimen is labeled with its thickness and test type. The inch-drawn is used to apply a tensile force to samples at a pull rate of 1 millimeter per minute and held samples with a grip pressure of 1600 psi. Acoustic emissions are detected as the sample is pulled apart. The piezoelectric sensors are attached to the sample at various locations to detect vibrations caused by microfractures. Our tests also utilize digital image correlation, or DIC, to capture displacement data at a capture rate of 1 frame per second, and this data will be used in the future to extrapolate more information. Our specimens are first prepped by cutting the laminate PMC into straight-edge sections. After this is done, either a hole or a notch is placed into our specimens corresponding to our DOE. Each specimen is then tabbed on each end, allowing the inch-drawn to properly grip the specimen. A section area is painted along the area of the hole or notch for the DIC to track displacement propagation. Once the sample is prepped, it is placed into the inch-drawn, it is clamped onto the grips, and sensors are placed onto the sample. The sensors are connected to Wave Explorer to collect our data, and the DIC is focused on the painted area of the sample. The DIC, inch-drawn, and Wave Explorer then simultaneously run to collect our data. Once the specimen breaks, the test is repeated for the other samples. Here you can see one of our samples being fractured. This is for a double notch test. The white stripe of paint that is overlapping the notches is used by the DIC to collect the propagation data we talked about earlier. Here you can see a flowchart of how the analysis for the project went. The files collected during the test using the Wave Explorer software are binary. They need to be converted into ASCII files so that they can be used by the Wave processor analysis tool. Wave Explorer has a useful tool called Wave Utility and easily converts binary to ASCII. Then these files can be opened in Wave Explorer. From there, you can choose an automated method for finding the TOA for each AE event at each sensor. We initially chose an automated method that finds the TOA once the amplitude of the wave file reached a specified threshold. Because many of our events were so small in amplitude, we set a threshold of 15 millivolts. From there, the software has an option that allows manual adjustment of the TOA as needed. We did this for all of the data files to get the most accurate results. These values can then be exported as text files from the software and then opened in Excel for further analysis. In addition to exporting the TOAs, we also exported the energy, peak frequency, and frequency centroid values for each of the AE events at each sensor. This information is important as it will be able to tell us how the AE event or wave attenuates across the sample. Since each set of samples has a different thickness and ply layout, we can draw conclusions with this information about how the geometry and architecture affects the acoustic emission events. We complete the rest of the analysis in Excel. Then we use the manual TOA values to sort out which sensor the AE event reached first. From this, we can decipher whether the event came from the gauge section of the sample or from the portion of the sample in the hydraulic grips. We then sort the events into gauge and grip events. From there, we can plot the energy, peak frequency, and frequency centroid against sensor distance to make our final conclusions. At the time of recording this video, our project is not yet finished, and we are unable to state the results of our extensive research and testing. But here we have summarized some of our next steps. So we're currently going through the analysis portion of our project, and we should be finished here shortly. And after this, we will discuss and make any conclusions we can about what our research has shown. Then we will compile all of our results and findings into our final paper. So just some final thoughts. We wanted to say thank you to everyone who helped us out with this project, and specifically thank you to Dr. Morsher for giving us the project and giving us your guidance every step of the way. Thank you to Dr. Vijay Pujar of Collins Aerospace in San Diego for providing us the materials, and thank you to Dr. Manny for helping us manufacture our samples, also providing your guidance and giving us some leniency with deadlines as well. That helped a lot. And thank you to the viewer for watching.